Imagine you're standing on a beach, toes sinking into warm sand, the salty breeze tugging at your shirt, and you toss a pebble into the surf. It arcs, slows, then kisses the water with a gentle plop. Why does it fall? Why does the moon stay aloft while the pebble surrenders to the sea? The answer, dear viewer, is gravity, the invisible handshake that binds apples to Earth, planets to suns, and galaxies to each other. Today on What Is, we're going to peel back the layers of this cosmic force, from the whimsical musings of ancient thinkers to the mind-bending equations of modern physics, with a sprinkle of humor to keep things from getting too, well, grounded. We're about to fall into the story of gravity. If you've ever wondered why you don't float off your couch when you binge watch your favorite show, or why astronauts appear to be in a perpetual slow-motion dance inside the International Space Station, you've already brushed shoulders with gravity's secretive personality. It's the ultimate clingy friend. Always there, never asking for permission, and somehow managing to keep the entire universe from spiraling into chaos. But gravity isn't just a simple, what goes up must come down rule. It's a saga that stretches across millennia, filled with brilliant blunders, daring experiments, and a few aha moments that would make even the most stoic physicists crack a smile. So let's dust off the chalkboards, fire up the imagination, and embark on a chronological joyride through humanity's quest to answer the deceptively simple question: what is gravity? Ancient foundations. Our tale begins in the dusty courtyards of ancient Greece, where philosophers liked to ponder the nature of motion while sipping wine and debating whether the world was flat or a giant leather ball. Aristotle, the big-name thinker of the 4th century BCE, claimed that objects fell because they sought their natural place: earth toward the center, water a bit higher, air above that, and fire craving the heavens. In his view, heavier things fell faster because they were more earthy. It sounded logical, until you tried dropping a feather and a hammer side by side. Spoiler, they didn't race. The feather floated lazily while the hammer plummeted, exposing a flaw in Aristotle's earth-centric logic. Enter the Hellenistic astronomer Hipparchus, who, while mapping stars, noticed that celestial bodies didn't plummet to Earth. They clung to their orbits like cosmic ballet dancers. He hinted that something kept them aloft, though he lacked the vocabulary to call it gravity. Fast forward to the Islamic Golden Age, where scholars like al-Biruni and Ibn Sina, Avicenna, began questioning Aristotle's natural place theory. Al-Biruni, ever the meticulous measurer, attempted to calculate Earth's radius using mountain shadows, a feat that would later prove crucial for understanding gravitational acceleration. Yet even these sharp minds clung to the idea that celestial motions were governed by a different set of rules than earthly fall, a dichotomy that would persist for centuries. Medieval musings. The Middle Ages saw a blend of Aristotelian philosophy and theological thought. In the West, scholars like Thomas Aquinas fused Aristotle's physics with Christian doctrine, reinforcing the notion that objects move toward their divinely ordained places. Meanwhile, in the Islamic world, thinkers such as Al-Ghazali explored causality, suggesting that God's will could be the underlying cause of motion, a precursor to the idea of a universal force, though still couched in theological language. It wasn't until the Renaissance that the shackles of pure Aristotelianism began to loosen. Nicholas Copernicus, daring to place the sun at the center of the cosmos, indirectly challenged the idea that Earth was the unique center of natural motion. His heliocentric model set the stage for a new question: if Earth isn't special, why do objects still fall toward it? Galileo's Leaning Tower, enter Galileo Galilei, the Italian polymath with a penchant for experimentation and a flair for drama. In the early 1600s, Galileo reportedly climbed the Leaning Tower of Pisa, though historians debate whether he actually dropped objects from the top or simply rolled them down inclined planes to test Aristotle's claim about falling speeds. His ingenious solution? Use a smooth inclined plane to slow down the motion, making timing easier with the water clocks of the day. By rolling balls of different masses down the same slope, Galileo discovered that, neglecting air resistance and friction, they accelerated at the same rate. He articulated this insight in his work, Discourses and Mathematical Demonstrations Relating to Two New Sciences, stating that the distance traveled by a falling object is proportional to the square of the time elapsed. The famous d equals 1/2 gt squared law, where g is the acceleration due to gravity. Galileo's experiments didn't just refute Aristotle, they laid the groundwork for a quantitative description of gravity, transforming it from a philosophical notion into something you could measure, predict, and crucially, doubt. Galileo also turned his telescope to the heavens, observing the moons of Jupiter dancing around their parent planet. He realized that if Jupiter could hold moons in orbit, perhaps Earth could hold the moon, hinting at a universal principle linking celestial and terrestrial motion. Yet Galileo stopped short of naming the force. He described the motions mathematically, but left the why to future. As for why the planets move so, we must seek a deeper cause. Open. Kepler's elliptical whisper. While Galileo was busy with inclined planes, Johannes Kepler was poring over the meticulous planetary observations of Tycho Brahe. Kepler's 3 laws of planetary motion, published between 1609 and 1619, revealed that planets travel in elliptical orbits with the Sun at one focus, sweep out equal areas in equal times, and that the square of a planet's orbital period is proportional to the cube of its semi-major axis. These laws were descriptive gems, but they beg the question, what force makes planets follow these precise paths? Kepler himself toyed with the idea of a magnetic influence emanating from the Sun, but magnetism fell short when applied to the outer planets. Still, his laws provided the essential scaffold upon which Isaac Newton would later build his universal law of gravitation. Newton's apple and the myth. Now we arrive at the legendary moment, whether true or embellished, of Sir Isaac Newton sitting under an apple tree, watching a fruit fall, and suddenly grasping that the same force pulling the apple to Earth also governs the moon's orbit. Whether the apple actually bonked Newton on the head is debatable, but the insight is historic. In 1687, Newton published Philosophiae Naturalis Principia Mathematica, commonly known as the Principia. Within its pages, he introduced 3 laws of motion, and most famously for our story, the law of universal gravitation. Every point mass attracts every other point mass, with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Mathematically, F equals G times m 1 times m2 over r squared, where F is the gravitational force, m1 and m2 are the masses, r is the distance between them, and g is the gravitational constant, a proportionality factor that Newton could not determine experimentally, but whose value we now know to be approximately 6.67430 times 10 to the minus 11 Newton meters squared per kilogram squared. Newton's brilliance lay in unifying celestial and terrestrial mechanics under a single mathematical framework. He showed that the same inverse square law that made an apple fall at 9.8 meters per second, squared on Earth's surface, also kept the moon in its orbit, causing it to fall toward Earth continuously, but with sufficient tangential velocity to perpetually miss, resulting in a stable orbit. Newton also tackled the problem of the gravitational constant indirectly through his work on the motion of the moon and the tides. By comparing the lunar orbital period with the known radius of Earth's orbit, he could infer the ratio of Earth's mass to the Sun's, laying groundwork for later measurements of g. The Principia didn't just explain why apples fall, it predicted the existence of Neptune, though its discovery came later, accounted for the precession of the equinoxes, and provided a framework that would dominate physics for over 2 centuries. Yet Newton himself was uneasy about the philosophical implications of action at a distance. How could 2 objects influence each other across empty space without any medium? He famously wrote, "I feign no hypotheses," acknowledging that while his equations worked, the underlying mechanism remained a mystery. If you're finding this journey through the ages of gravity as fascinating as a falling apple in slow motion, why not give this video a thumbs up? It helps the channel grow and lets us bring more deep dives like this one. And if you haven't already, consider subscribing. We've got a whole universe of what is episodes waiting to explode into your feed. The constant G. Speaking of the gravitational constant G, its measurement became a holy grail for experimental physicists. The first successful laboratory determination came from Henry Cavendish in 1798, using a torsion balance, a delicate device consisting of a horizontal bar suspended from a thin wire with small lead spheres attached to its ends. Larger lead spheres were placed nearby, and their gravitational pull caused the bar to twist ever so slightly. By measuring the angle of twist and knowing the torsion constant of the wire, Cavendish could calculate the force between the masses, and consequently, G. His result, G approximately equals 6.754 times 10 to the power of minus 11, Newton meters squared per kilogram squared, was within about 1% of today's accepted value, a stunning achievement given the equipment of the 18th century. Cavendish's experiment not only quantified G, but also allowed the calculation of Earth's mass. Knowing G, the gravitational acceleration at Earth's surface, G, and Earth's radius, one can solve for m sub e equals gr squared over g. This turned gravity from a celestial curiosity into a tool for probing the very makeup of our planet. Einstein's revolution. Fast forward to the early 20th century, when Albert Einstein, working as a patent clerk in Bern, began to question the very foundations of Newtonian gravity. Newton's inverse square law worked splendidly for most everyday scenarios, but it faltered under extreme conditions, such as the orbit of Mercury, which displayed a tiny but persistent precession that Newtonian mechanics couldn't fully account for. Einstein's breakthrough came not from a new force, but from a radical reimagining of spacetime itself. In 1915, he presented the general theory of relativity, encapsulated by the Einstein field equations. G mu nu plus lambda G mu nu equals 8 pi G over c to the fourth times T mu nu. Here, G mu nu represents the curvature of spacetime open parenthesis, the Einstein tensor close parenthesis. Lambda is the cosmological constant. G mu nu is the metric tensor describing the geometry of spacetime. T mu nu is the stress energy tensor encoding matter and energy. G is the gravitational constant, and c is the speed of light. In plain language, mass and energy tell spacetime how to curve. Curved spacetime tells mass and energy how to move. Gravity, therefore, isn't a mysterious force acting at a distance. It's the manifestation of geometry. A planet orbiting a star isn't being pulled by an invisible string. It's following the straightest possible path, a geodesic, through curved spacetime created by the star's mass. Einstein's theory made several astonishing predictions that Newton's could not. The bending of light by massive bodies, observed during the 1919 solar eclipse, the gravitational redshift of light climbing out of a gravitational well, and the existence of gravitational waves, ripples in spacetime propagating at the speed of light. The 1919 eclipse expedition, led by Arthur Eddington, measured the apparent shift of star positions near the Sun's limb and found agreement with Einstein's predicted deflection of 1.75 arcseconds, catapulting him to international fame. General relativity also introduced the concept of black holes, regions where spacetime curvature becomes so extreme that not even light can escape. The Schwarzschild solution, derived shortly after Einstein's publication, described the spacetime around a spherically symmetric, non-rotating mass. Decades later, observations of X-ray binaries and the Event Horizon Telescope's image of M87 star would provide empirical support for these cosmic monsters. Yet even Einstein's masterpiece left questions unanswered. How does gravity fit with the other three fundamental forces? Electromagnetism, the strong nuclear force, and the weak nuclear force, which are all described by quantum field theories. And what about the cosmological constant lambda, which Einstein initially added to allow a static universe, later called it his biggest blunder, only to see it resurrected as a possible explanation for dark energy driving the accelerated expansion of the universe? Quantum gravity, the ongoing quest. The marriage of gravity with quantum mechanics remains one of the greatest unsolved puzzles in physics. Quantum field theory excels at describing the other three forces through the exchange of force-carrying particles: photons for electromagnetism, gluons for the strong force, and W/Z bosons for the weak force. For gravity, the analogous hypothetical particle is the graviton, a massless spin-2 boson that would mediate gravitational interactions in a quantum framework. However, attempts to quantize gravity using the same techniques that succeeded for other forces run into severe difficulties. When you try to apply quantum field theory to the gravitational field, the resulting equations produce infinities that cannot be removed through the standard renormalization procedures. In other words, the theory predicts probabilities greater than 1 or nonsensical results at very high energies, a sign that our current approach breaks down. Enter string theory, proposed in the late 1960s and early 1970s as a way to describe particles not as point-like entities, but as tiny, vibrating strings. Remarkably, string theory naturally includes a spin-2 massless excitation that behaves like a graviton, offering a potential unified description of all forces, including gravity. The theory requires extra spatial dimensions, typically 6 or 7 compactified dimensions beyond the familiar 3, leading to a rich landscape of possible universes, often referred to as the string landscape. Another prominent contender is loop quantum gravity, LQG, which takes a different route. Instead of starting with strings, LQG quantizes spacetime itself. It envisions space as composed of discrete, finite loops woven together into a spin network. Areas and volumes become quantized, meaning there is a smallest possible unit of area and volume, a Planck scale granularity. In LQG, gravity emerges from the dynamics of these spin networks, providing a background-independent framework where spacetime is not a stage, but a participant. Both approaches have yielded insights. String theory has given us tools like holography, the ADS/CFT correspondence, suggesting a deep connection between gravity in a volume and quantum field theory on its boundary. Loop quantum gravity has produced concrete predictions for the discrete structure of spacetime that could, in principle, be probed by high-energy cosmic rays or gravitational wave observations. Yet neither theory has produced a definitive, experimentally verified prediction that distinguishes it from the others or from pure general relativity inaccessible phenomena. The search continues, with experiments like LIGO/Virgo detecting gravitational waves, satellite missions testing the equivalence principle to unprecedented precision, and tabletop experiments probing for deviations from Newton's inverse square law at sub-millimeter scales, all hunting for cracks in our current understanding that might point toward quantum gravity. Modern experiments and applications. Beyond the theoretical quest, gravity's influence permeates modern technology and cosmology. Global Positioning System, GPS, satellites must account for both special and relativistic time dilation. Clocks aboard the satellites run faster by about 38 microseconds per day due to weaker gravitational potential at altitude. Without correction, GPS positions would drift by kilometers each day. Gravitational lensing, the bending of light by massive clusters, acts as nature's telescope, allowing astronomers to glimpse distant galaxies, otherwise too faint to observe. The study of galaxy rotation curves and the gravitational dynamics of clusters led to the hypothesis of dark matter, an invisible substance that contributes roughly 27% of the universe's energy density, inferred solely from its gravitational effects. On the cosmological scale, the observed accelerated expansion of the universe, discovered via Type 1a supernovae in the late 1990s, suggests the presence of dark energy, a repulsive gravitational effect often associated with Einstein's cosmological constant lambda. Understanding whether lambda truly is a constant or a dynamical field remains a frontier of modern cosmology. Closer to home, precision measurements of G continue to challenge physicists. Recent experiments using atom interferometry, laser range measurements, and improved torsion balances have yielded values of G that differ by more than the quoted uncertainties, sparking debates about possible hidden systematic errors or even new physics. And let's not forget the playful side. Astronauts aboard the ISS experience microgravity, allowing them to perform graceful flips, drink floating water blobs, and grow crystals that reveal novel structures impossible under Earth's gravity. These demonstrations not only inspire the public, but also provide unique environments for studying fluid dynamics, combustion, and material science in ways that ground-based labs cannot replicate. Now let's swing back to the human side of gravity, the stories of the scientists who dared to question, experiment, and sometimes fail spectacularly. Take the tale of the Cavendish experiment. Henry Cavendish, notoriously shy, conducted his landmark torsion balance test in a sealed room to avoid drafts, all while barely speaking to his assistants. His meticulous notes, hidden away for decades, were only rediscovered later, revealing a man who preferred the quiet company of his apparatus to the limelight of scientific fame. Then there's the story of Arthur Eddington's 1919 eclipse expedition. Eddington, a pacifist Quaker, faced logistical nightmares, transporting fragile telescopes to the island of Principe off West Africa, battling tropical weather, and negotiating with local authorities. When the eclipse finally arrived, clouds threatened to ruin the observations, but a brief clearing allowed Eddington's team to capture the crucial plates that would later confirm Einstein's prediction. His quiet determination exemplified how curiosity can triumph over adversity. Fast forward to the modern era, where the LIGO scientific collaboration, thousands of scientists spread across the globe, spent decades building laser interferometers capable of measuring changes in distance smaller than a proton's width. When the first gravitational wave arrived on September 14, 2015, produced by the merger of two black holes over 1 billion light-years away, the signal rippled through the detectors like a cosmic heartbeat, confirming a century-old prediction and opening a new window onto the universe. These human narratives remind us that gravity, while a fundamental force of nature, is also deeply intertwined with the perseverance, creativity, and occasional quirkiness of those who seek to understand it. Before we wrap up, if you've enjoyed this epic tale of falling apples, bending space-time, and cosmic whispers, please smash that subscribe button, ring the notification bell, and share this video with anyone who looks up at the night sky and wonders what's holding it all together. Your support fuels more research-filled, fun-packed episodes and helps us keep exploring the mysteries of the universe, one what is at a time. Bonus fact. And now, for a bonus nugget that didn't fit elsewhere. Did you know that if you could somehow compress the entire mass of the observable universe into a sphere, its radius would be about 13.8 billion light-years, roughly the same as the age of the universe in light-years? This coincidence arises because the observable universe's average density is just shy of the critical density needed to halt its expansion, making the cosmos delicately balanced between eternal expansion and eventual collapse. In other words, the universe is poised on the knife edge of gravity's tug, a cosmic tightrope act that keeps us guessing about its ultimate fate. Thanks for watching. Keep questioning, keep exploring, and remember, gravity may hold us down, but curiosity lifts us higher. See you next time.